This is our second of 4 lectures about calculus. In the previous lecture, we talked about limits, continuity, and what a derivative means. This week, we're going to talk about how we can calculate the derivative of some functions. We're going to cover chapters 27, 28, and 29 of the lecture notes. Let's start with some rules. Easiest type of function is a constant function. K is a number, then the derivative of the number k is 0. We have a power function. That's a function of the form x to the power n. The rule is that the derivative of x to the power n is n multiplied by x to the power n minus 1. For example, the derivative of x cubed is 3 multiplied by x to the power 3 minus 1, or 3x squared. We can do the derivative of the square root of x using the same way, because the square root of x is the same as x to the power of a half. Using our rule, this is a half x to the power of a half minus 1, or half x to the power minus a half, which is the same as 1 divided by 2 square root of x. Or we can do the derivative of, for example, 1 divided by x to the power 4, because 1 divided by x to the power 4 is the same as x to the power minus 4. Using the same idea, we get the answer minus 4 x to the power minus 4 minus 1, which is the same as minus 4 divided by x to the power 5. Next rule, the constant multiple rule. If we know that u is a differentiable function, and if we know that k is a number, then if we try to calculate the derivative of k multiplied by u, we can take the number k and we can move this outside of the derivative. The derivative of ku is the same as k multiplied by the derivative of u. This rule I'm going to give a proof of, because it's a nice, easy proof that they're all proved in a similar way, but some are more difficult than others. We'll start by writing down the definition of the derivative of ku. That's the same as saying that the limit as h tends to 0 of k multiplied by u at x plus h minus k multiplied by ux divided by h. Using the constant multiple rule for limits, we can take this number k and we can move this off the limit. So we get k multiplied by a limit, but this limit is, of course, is just the same as the derivative of u. So we get k multiplied by du dx. For example, if I want to calculate the derivative of 3x squared, using the constant multiple rule, we can take the number 3 outside. This is the same as 3 multiplied by the derivative of x squared. Or if I want to calculate the derivative of minus u, we can take a factor of minus 1 outside of the derivative. This is the same as minus 1 multiplied by the derivative of u. Our next rule is the sum rule. If we have two functions u and v, which are differentiable at the starting point x0, then their sum is also differentiable at this point, and the derivative of u plus v is the same as the derivative of u plus the derivative of v. For example, let's suppose we want to differentiate x cubed plus 4 over 3x squared minus 5x plus 1. What we can do is we can take this function, and then using the sum rule, we can split this into 4 easier derivatives. Next example, does the curve y is equal to x to the power 4 minus 2x squared plus 2 have any points where the derivative is equal to, or the slope is equal to 0? And if so, where are these points? We start by calculating the derivative of y. Of course, this is the same as 4x cubed minus 4x, which we can factor to 4x multiplied by x minus 1 multiplied by x plus 1. And then we can ask, how do we get that this is equal to 0? This is 0 if x is 0. It's 0 if x minus 1 is 0, in other words, if x is 1. Or it's 0 if x plus 1 is equal to 0. In other words, if x is equal to minus 1. So this is 0 if and only if x is minus 1 or 0 or 1. Here's a graph of this function. We can see that the graph has slope 0 when x is equal to minus 1, has slope 0 when x is equal to 0, and has slope 0 when x is equal to 1. The product rule. Again, let's suppose we have two functions u and v, which are both differentiable at the point x0. Then the product of u and v is also differentiable at this point, and we have a formula to calculate this derivative. We've written in two different ways, using D'Alembert's notation and using prime notation. For example, using prime notation, we have the formula that the derivative of uv is equal to the derivative of u multiplied by v plus u multiplied by the derivative of v. If you want to, you could write a proof of this using the definition of derivative, which is the definition using limits. But for us, we are interested in how we can use this to, for example, differentiate a function like this. Differentiate x squared plus 1 multiplied by x cubed plus 3. And I'm going to solve this in two different ways. First of all, I'm going to solve this using the product rule, because we have y is equal to u multiplied by v, where u is the function x squared plus 1, and v is the function x cubed plus 3. So using the product rule, first we differentiate the first function, and we leave the second function exactly the same. And then we do plus, and then the first function we leave as it is, and we differentiate the second function. The derivative of x squared plus 1, of course, is 2x plus 0. And the derivative of x cubed plus 3, of course, is 3x squared plus 0. When we multiply this out, we get the answer 5x to the power 4 plus 3x squared plus 6x. Or we can solve this problem another way. We might decide first we're going to multiply these two brackets together to get x to the power 5 plus x cubed plus 3x squared plus 3, and then differentiate this to get exactly the same answer, 5x to the power 4 plus 3x squared plus 6x plus 0. For an easy function like this, it doesn't matter which method we use, we get the same answer. If we had more complicated functions, a complicated function multiplied by a more complicated function, we would need to use the product rule. Next rule, the quotient rule. Let's suppose u and v are functions which are both differentiable at the point x0. And one more condition, just to be careful. Let's suppose that v at x0 is not equal to 0, because we don't want to be dividing by 0. Then u divided by v is also differentiable at the point x0, and we have a formula for the derivative of u divided by v. It's u prime v minus u v prime divided by v squared. Let me just remind you of the product rule. The derivative of u multiplied by v also started as u prime v, but then it was plus uv prime. For the quotient rule, we have a minus sign instead of a plus sign, and we must divide by v squared. For example, we could use the quotient rule to calculate this derivative. Differentiate t squared minus 1 divided by t cubed plus 4. We have a function divided by a function. The function on the top is t squared minus 1, and the function on the bottom is t cubed plus 1. We're going to use the quotient rule. We're going to use the formula u prime v minus uv prime divided by v squared. I'll leave it for you to pause the video at this point and check that you're happy with this calculation. Check that you're happy that this is the correct answer. Moving on, we can do another example. Differentiate square root of s minus 1 divided by the square root of s plus 1. Again, we have function divided by function. Function on the top is square root of s minus 1, and the function on the bottom is square root of s plus 1. And let me remind you, we've already seen the derivative of the square root of a variable. So let me just remind you, we've seen earlier today, earlier in this lesson, that this derivative is 1 divided by 2 square root of s. We can use the quotient rule to calculate this derivative. We must calculate u prime v minus uv prime divided by v squared. Again, please pause the video and check this calculation, check that you're happy with this, and then let's move on. Second order derivatives. If we start with a function f, which is a differentiable function, we differentiate it, then we get a new function called f prime. Sometimes f prime is also differentiable, and we can differentiate it a second time. If we differentiate a second time, we get a third function, which we call f double prime. F double prime is called the second derivative of f, and we can write it like this. We can write f double prime x. This is the same as the derivative of f prime, or the derivative of the derivative of y, or d squared y dx squared, or dy prime dx, or y double prime. For example, let's suppose we have y is equal to x to the power 6, and we want to calculate the second derivative of this function. First, we must calculate the first derivative. There's no shortcuts here. We must do the first derivative first, then the second derivative. The first derivative is 6x to the power 5, and then we can differentiate a second time to get the second derivative, 30x to the power 4. And we can continue with this idea. If f double prime is a differentiable function, then we can differentiate it to find a new function, which we call f triple prime. This is the third derivative of f. If the third derivative of f is differentiable, then its derivative is called the fourth derivative of f, and so on. if the fourth derivative of f is differentiable, then its derivative is the fifth derivative of f, and so on. Before I go on, let's suppose we're looking at, say, the 13th derivative of f. The way we usually write this is f superscript open brackets 13 close bracket. And we write this because if this is more sensible than writing f prime 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 prime, because of course this is just silly. So the usual convention is for the first three derivatives we use the prime notation, prime, double prime, and triple prime. And then as soon as we get to the fourth derivative and going onwards, we switch to numbers in brackets. For example, find the first four derivatives of x cubed minus 3x squared plus 2. This is an easy function. You can just use the power rule, the sum rule, the constant multiple rule to calculate these derivatives. First derivative, 3x squared minus cx. Differentiate again. Second derivative, 6x minus 6. Differentiate a third time. The third derivative is 6. Differentiate a constant number 6, we get 0. The fourth derivative is 0. And let me just note, because the derivative of 0 is 0, we also know that the fifth derivative is 0, the sixth derivative is 0, the seventh derivative is 0, and so on. We can look at the derivatives of the trigonometric functions. Two rules to memorize. The derivative of sine is cos, and the derivative of cos is minus sine. For example, differentiate x squared minus sine x. The derivative of x squared is 2x, and the derivative of sine x is cos x. So the answer is 2x minus cos x. Differentiate x squared sine x. This time we need to use the product rule because we have a function multiplied by a function. So we're going to be calculating the derivative of x squared multiplied by sine x plus x squared multiplied by the derivative of sine x. And we get the answer 2x sine x plus x squared cos x. Now a quotient rule example. Differentiate sine x divided by x. Using the quotient rule, we can calculate this as x cos x minus sine x divided by x squared. The derivative of cos x is minus sine x, so the derivative of 5x plus cos x must be 5 minus sine x. Differentiate sine x cos x. This time we need to use the product rule. Derivative of sine multiplied by cos plus sine multiplied by the derivative of cos. We get cos cos plus sine multiplied by minus sine, or cos squared minus sine squared. Another quotient rule example. Differentiate cos x divided by 1 minus sine x. Using the quotient rule, we have the derivative of the top multiplied by the bottom minus the top multiplied by the derivative of the bottom, and then divided by the bottom squared. And I'll leave it for you to pause the video, quickly look through this calculation, check that you're happy with this, and then let's continue. The tangent function. The derivative of tan is sec squared x. This rule I'm going to prove. We can prove this using the quotient rule because tan is the same as sine divided by cos. Anytime we have function divided by function, we can use the quotient rule. We have the derivative of sine multiplied by cos minus sine divided by the derivative of cos divided by cos squared. The derivative of sine, of course, is cos, and the derivative of cos, of course, is minus sine. So we end up with cos squared plus sine squared, which of course we know is 1, divided by cos squared. We get 1 divided by cos squared, but that's the same as sec squared. You should be able to do a proof like this if I ask you. The other three trigonometric functions. The derivative of sec is sec x tan x. The derivative of cotan x is minus cosec squared x. The derivative of cosec x is minus cosec x cotan x. Exactly the same way that we proved that the derivative of tan was sec squared, you can use the quotient rule to prove these three rules. Some years I ask you to prove one of these in exam, some years I don't ask you to do this in exam. But just in case this year is one of the years that I decide to put this on the final exam, have a practice with these three proofs before the exam. For example, now that we have these rules, we can calculate some functions. Find y double prime, the second derivative of y, if y is equal to sec x. We have the rule that the derivative of sec is sec x tan x. So the second derivative of y must be the derivative of sec x tan x. We use the product rule. The derivative of sec multiplied by tan plus sec multiplied by the derivative of tan. Put the formula in. The derivative of sec is sec tan, and the derivative of tan is sec squared. We end up with the answer sec x tan x squared plus sec cubed x. And the final chapter that I'm talking about today is the chain rule. For example, the question we might be interested in asking is, how do we differentiate a function such as sine of x squared minus 4? How do we differentiate a function which is a function of a function? We use a rule called the chain rule. Suppose that we have two functions, f and g. Suppose that f is differentiable at the point u and g is differentiable at the point x. Then f composed of g is differentiable at x, and we have our formula. The derivative of f composed of g is the same as the derivative of f calculated at g of x multiplied by the derivative of g at x. If we use Leibniz's notation, this is perhaps easier to remember. dy dx divide dy du multiplied by du dx. And I think this is easy to remember because if we think of a derivative as dy divided by du and du divided by dx, then we might imagine that the du's can cancel and we end up with dy dx. For example, the question I started the chapter with, differentiate sine of x squared minus 4. Let's look at this function. We have y is equal to sine of u, where u is the function x squared minus 4. We have a function of a function. So we use the chain rule. We can differentiate these two easier functions. The derivative of sine u with respect to u is cos u, and the derivative of x squared minus 4 with respect to x is 2x. So, using the chain rule says dy dx is the same as dy du multiplied by du dx. So what we're doing is we're doing cos u multiplied by 2x. Or to say it another way, we have 2x multiplied by cos u. The final step is to replace u by x squared minus 4. The answer to this problem is 2x cos x squared minus 4. Before I go on, in maths, if we use a rule, we need to say that we're using the rule. In this calculation, we've used the chain rule, so in my answer, I need to write by the chain rule. Next example, differentiate sine of x squared plus 4. First thing we need to do is we need to choose a u. We want to look at our function and we want to choose some function u which will make this into two easy functions. For this problem, I'm going to choose u is equal to x squared plus x. Then we have our function sine of u and u of x squared plus x. We can use the chain rule to see that this is the same as du of sine u multiplied by du dx. Again, we could just pretend that this is the same as du cancels with du, and we end up with d sine u on top and dx on the bottom. It's not what it really means, but we can imagine that it means this. We go through the calculation and we end up with 2x plus 1 multiplied by cos x squared plus x. And again, because we've used the chain rule, we must write by the chain rule in our answer. Sometimes we need to use the chain rule twice or more times. In this example, we're going to need to use the chain rule 2 times. Differentiate the function g of t, which is equal to tan of 5 minus sine of 2t. Step 1 is to choose a function u, which will simplify this. We choose u is 5 minus sine 2t. Then we have the easier function g of t is equal to tan u. And we can calculate this derivative using the chain rule. du dt is the same as dg du dt, or sec squared u multiplied by the derivative of 5 minus sine 2t. We need to find the derivative of 5 minus sine 2t, so we're going to need to use the chain rule a second time. I've already used the letter u. I need the new letter. I'm choosing to use the letter W now. Doesn't matter which letter we use, as long as it's not T or U. So just choose a new letter. I'm going to let W be equal to 2T. Then clearly there's a mistake here. The derivative of 5 minus sine 2t is the same as ddw of 5 minus sine w dw dt, or minus cos w multiplied by 2. And I'll leave it for you to check that the final answer is minus 2 cos 2t sec squared 5 minus sine 2t. Let me just remark before we go on. The final answer should not have u or w in it. U and w are variables that we use in the middle of our calculation. The final answer, we need to substitute back in our functions. We can also use the chain rule to calculate powers of a function. Now, let me remind you the chain rule. The chain rule says dy dx is the same as dy du or du dx. That's the same as saying the derivative of f of u is f prime of u multiplied by du dx. In this section, let's suppose that f of u is always u to the power n for some number n. And we know the derivative of this, of course. We know that f prime of u is n multiplied by u to the power n minus 1. So the chain rule tells us that d dx of u to the power n is n multiplied by u to the power n minus 1 multiplied by du dx. In the next few examples, we're going to be using this formula. For example, d dx of 5x cubed minus x to the power 4, all to the power 7. In this example, we're going to have u is 5x cubed minus x to the power 4. And then we're going to be doing d dx of u to the power 7, which of course is 7u to the power 6, and then multiplied by du dx. So that's 7 5x cubed minus x4 is our u to the power 6, and then multiplied by the derivative of u, or the derivative of 5x to the power 3 minus x to the power 4. Another example. Differentiate 1 over 3x minus 2. Again, we have a power function because 1 divided by 3x minus 2 is the same as 3x minus 2 to the power minus 1. We have the derivative of some function u to the power minus 1. So of course it's minus 1, u to the power minus 2, and then du dx, or minus 1, 3x minus 2 to the power minus 2, d dx of 3x minus 2. And you can check the rest of this calculation. For example, the derivative of sine to the power 5 of x. We have u equal to sine of x, and we're doing the d dx of u to the power 5. Using our rule, we can see this is the same as 5 sine to the power of 4 of x multiplied by the derivative of sine x. We can also use this to differentiate the absolute value of x. We've looked at this before.